Okay, so here's a little video about cosets and Lagrange's theorem. It's really, really important stuff. So we have a group G, and here we have an H, which is a subgroup of G, and that's all we're assuming about H right now. Later on, we'll have normal subgroups, but that's not what we're interested in right now. And basically what we're going to do is we're going to take G, and I'm going to, view G as a ball, and we're going to break it up into pieces. We're going to get a partition. Okay, I'm sort of telling you what we're going to do before we do it. One of the pieces will be H, okay, and the other pieces in here will be things called cosets. So they'll be of the form, GH, maybe G prime H. So it'll be like that. So it'll be H, and then H moved around by various elements of G, right? So the way this is going to go is we define an equivalence relation. We define a relation. A is equivalent to B, say mod H, if and only if. And there's two ways of doing this, and I'm going to just say, let's see, the way I'm going to do it is B inverse A is an element of H. Okay, so I'm going to do it like that. And let's see, let's show that this is an equivalence relation. Okay, so A is equivalent to A. I'm going to leave off the H when it's kind of clear. And this is because, A inverse A is E and E is an H, right? So I'll just check that one off. A is equivalent to B, is equivalent to C. Well, so what does this turn into? This turns into B inverse A is an element of H, and it turns into C inverse B is an element of H. Okay, so we can just do this. We can say then B, let's see, so sorry, let's do it the other way. So let's do this. C inverse B, B inverse A, right, is definitely C inverse A. And these are both in H, so this is in H, right? And so this says that A is equivalent to C, right? So we got that A is equivalent to B, B is equivalent to C, implies A is equivalent to C. So that's symmetry. That's transitivity. And then A is equivalent to B, right? So that's gonna be if and only if B inverse A is an element of H. Okay, but then the inverse of that, so this will be if and only if B inverse A inverse element of H, but this is if and only if A inverse B, A, so you have to flip them around in inverse, and B inverse inverse, but that's just B, right? It's the element of H. Okay, so check, right? So this implies, well, this if and only if B inverse B is equivalent to A, right? Okay, so we have an equivalence relation, and we see that the equivalence, so we definitely have equivalence classes because we have an equivalence relation, right? So what do I want to say? So the equivalence class, so generally, right, the equivalence classes would be the set of all G, such that, let's see, the equivalence class of G would be, mod twiddle, right, would be the set of all G primes, such that G is equivalent to G prime, okay? And what I want to see is that this is actually just GH, right? So all the products G times things in H, right? So what's actually in here? So G prime is in G, if and only if G is equivalent to G prime. And now we know it doesn't matter which sort, whoops, G prime. Doesn't matter which order I write that in, right? Because of reflexivity. G prime, it doesn't matter if I write that. So this is if and only if G prime G is an element of H. Okay, so this is if and only if, sorry, G prime inverse. Actually, let me write this the other way around. In fact, just to make it clear, let me write this the other way around. Okay, so G prime is equivalent to G, right? So this will be G inverse G is an element of H. So this will be if and only if G inverse G prime is an element of H, right? So this will be if and only if G prime is an element of G, I multiply both sides by G, GH, right? And that's actually what I wanted, right? So something is in here, something's equivalent to G, if and only if G prime is in GH, right? So that's good. So this equivalence class is just G times things in H. So that's is what I said in the picture up there. And then we see this could be another definition for the equivalence too. So we could say, so we see from that G is equivalent to G prime if and only if GH is equal to G prime H, right? And so this is important because notice what we get here is we get that, we look at a GH and a G prime H, right? What do we know? We know that if GH intersect G prime H is non-empty, that meets it all, right? Then we know that GH equals G prime H. And this is just what it means to be a partition, right? Yeah, what else? So we know that the union of all the GHs is all of G, right, for G and G, okay? And we know then that, and one thing we know is that GH, the size, is actually equal to H. So let's see why that's true. And we'll just look at this map, phi goes from H to GH, and it's going to be the obvious thing. H gets mapped to GH, right? And clearly it's onto, just by definition of what GH is, and if GH equals GH prime, right, then I can multiply both sides by G inverse, and I get H equals H prime, right? So it's 1-to-1. So these two sets are the same. So all the sets are the same size, right? So again, taking this picture up here, I've just taken G, we've broken it into pieces, these equivalence classes. So this is G. One of these is H, right? So that'll be the equivalence class of H. And these other things are GH, and they all have the same size, right? So one thing that says immediately, right, is that the size of G, right, is the number of equivalence classes in here. So how do I want to write that? Well, let's make a definition. Okay, so G colon H equals the number of equivalence classes. And usually we don't just make up definitions like that, but this is a definition we need to know. So this would be G colon H, right, times the size of H, right? So the number of classes, each class has size H, right? So this gives us a kind of counting here. And notice as a corollary so we get here, if H is a subgroup of G, then the size of H divides the size of G. Now this is important. This is actually Lagrange's theorem. Lagrange. And this is really, really important. It's used to analyze like finite groups, used for all sorts of things. But I mean, one of the things it's used to do is to analyze finite groups. Okay. So this is obvious once we've done this calculation up here. Let's see. And one of the things Lagrange's theorem does, okay, so let's call this a theorem. This is the actual Lagrange's theorem right there. Let's get this corollary. If we take an element in G, right, then this is a subgroup, right? So we know that G, the order of G divides, oops, let's do it like this. We know that, we know that the order of G, of the subgroup generated by G, right? And so we call that the order of G. By the way, sometimes this is written as OG too. I think your book uses this, but actually now I'm not completely sure. But this will divide, because this is a subgroup, will divide the size of G, right? It's assuming G is a finite group, right? I guess if G is an infinite group, that's true too, but you got to think about what it means to divide an infinite number. So in particular, right, we know that, I mean, one thing you know is that G, right, to the order of G is E, right? Because that's what the order of G means, right? You go, you have, what was G? Let's just remind ourselves, right? This is E, G, etc., right, up to G, order of G minus 1, right? If you do one more, so you go up to G to the order of G, you get back to E again, right? So that's what happens. So this is E is equal to that. And since G divides the size of G, we know that G to the G, right, equals E. Okay. So, so really important. Let's see, one thing this does for us, right, is we can see that, you know, given n and z plus, right, we know that un is the set of things relatively prime to n, right? We know that. We know the size of un, right, is the Euler phi function, phi n, right? We know that this is a multiplicative group, right? So if we take m in here, right, we know the order of, we know m raised to the size of this group, right, is going to be 1, right? Because the e here is 1, right? And so this says that m to the phi n is equal to 1, right? So that's theorem, and I forget, this is maybe called Fermat's theorem. Sorry, it's easy for me to remember results, and names of results is harder, but it's basically this: m to the phi n is equal to 1 mod n for GCD mn equals 1, and we're only interested in m which are less than n. So m, you know, less than n. But you know, okay, 0 less than or equal to m less than n, right? Things in Zn, right? So this is used a lot, like in cryptography and stuff. Now there are number theoretic proofs. We're doing completely group theoretic proofs, right? But it just falls immediately out of Lagrange's theorem. So that's maybe the best proof. Let's see. I mentioned here the orbit stabilizer theorem. I'm going to actually have a different video on that sort of thing. And there's one last thing here, which is not really related to Cosets and Lagrange theorem, but it's a useful fact. And it's just that the size of HK. I mean, we'll do this when we have products later on, where one of these groups is normal. But here, nothing, and we don't even know what a normal group is now, maybe. But we say this is HK over the size of H intersect K. All right. Okay, and of course, to do this, what I want to do is take the products of things in HK and basically define classes again, you know, some sort of equivalence classes, and see that this works out just like we did above, right? So something like that. I'm going to pause for a sec. Let's see, I paused the recording briefly to think about this for a second, and I don't actually remember what I had written before, so let's just go through this. I'm trying to show that the size of HK is equal to the product of H and K over the size of the intersection of the H and K. And so it's clear that if I have these, that I define this equivalence relation, so HK is equivalent to H prime K prime if and only if HK equals H prime K prime, right? Because we're interested in when things that are different here, right? So in the cross product of H and K has the size of the product of these two sets. Okay, and so we can sort of work this down to, you know, multiply what both sides by H prime inverse. I get H prime inverse H equals, and then multiply both sides by K inverse, so K prime K inverse, right? Now this is clearly an H, it's equal to that. This is clearly in K, so this thing is clearly an HK, right? And then what I claim is that if I take, if I take a specific HK, right, inside of H cross K, and I look at G and H intersect K, and I look at the, you know, this map, G maps to HG G inverse K, right? Then clearly HK is equivalent to that thing there, right? So that's one thing. And this is actually 1-to-1, right? Because, right, if I had HG prime G prime inverse K equals HG G inverse K, right, like that, then I would have HG prime equals HG, right? And I would have, and that's enough already to multiply both sides by H and get that G prime equals G, right? So this is a one-to-one map. So this is a one-to-one map. And it's onto because I could just take, this side. If I take this side and multiply on the, let's see, if I take this one, right, and multiply, let's get the order right. Yeah, if I take this one and multiply by that, right, then I'm going to get H, right? And if I take this one and multiply on the right by the inverse of this, right, then I'll get K, right? So taking this to be G and making this operation on, I would get that thing there. So that gives me the onto. I'm kind of going in the backwards here because I'm going from this one to that one, right? But it's actually one-to-one and onto. And so this is showing, I mean, it's easy to see this as an equivalence class. So basically we're taking H cross K and we're breaking it into pieces, right? So maybe you can even here, you can sort of view this as H and this is K, right? We're kind of breaking it into pieces like that. And we're seeing that each piece is determined by the size of that. So actually all these pieces have size H intersect K, right? So it's kind of like the argument we had above, but this thing isn't a subgroup necessarily, right? It's just, a subset. So it's a useful thing. The book does some examples with it, but anyway, that's a good thing to know. And that'll be all for this part of the video. I'll just say the internal and direct end products. I have a video for a separate set of notes on that. So I'm just going to point to that video here. I don't have very much here, but I have quite a bit in that video and in those other notes. And then, so our next topic for video will be normal subgroups and factor groups. And I'll stop there.